Welcome to the inaugural lecture of Tsaftaris. My name is Ian Gordon. I'm the head of the College of Science and Engineering. I'm going to pass across to Gareth Harrison, the head of School of Engineering, who's going to introduce Sotos properly. Gareth.
Good evening, everybody. This is, I think, going to be a good one. At least I hope it's going to be a good one. You're all very welcome. There's quite a good number in the room and an even bigger number online. So you're all very welcome. I hope you enjoy the talk. My thanks to Louise Farquharson for arranging this. So it's my pleasure to introduce Sotos. I'm not going to use his full name. I think I will mangle that. But Sotos is our chair in machine learning and computer vision. And he also has a second, or sort of second chair, as the Canon Medical Royal Academy of Engineering Research Chair in Healthcare AI. He's a very esteemed guy. He's been around for a while. He's come here via US and Italy, the US and back to here. More degrees than I have, which is not a difficult thing. His PhD advisor from Northwestern, I believe, is online, so thank you very much to him. He's also joined by a good number of his family, his wife Christina, his daughters Sophia and Olivia, and his parents, Athanasios and Sophia. You're all very welcome, and yes, I hope you're going to cheer him along. So Sotos is going to tell us about the pixel takes it all. Good luck.
Thank you, Gareth. Thank you, everybody. So the first thing you all have to do is sing the song. You know the song of ABBA? No? That's the first test. You're all failing. This is a lecture room, after all. We do teaching here. Anyway, so thank you for coming today. So it's a very great pleasure to do this almost 5 years after I got the position. I'm actually glad that it happened after 5 years. I think I got better. In at least how I present, and I think how to make slides better. The theme of today, you will see there is a timeline. And this timeline will interject things that have happened in the field of computer vision and representation learning, starting from how we think that we process information in the brain, then how we move to the digital world, and how we try to do digital computer vision, and then how I have progressed as a scientist, working and trying to extract information out of different types of images, either art, agriculture, or even now recently with my team trying to do AI that can work like radiologists or think like radiologists. And I will end with my biggest undertaking today. So let's get started. We're going to go all the way back to the 1800s with the work on von Helmholtz, who basically said something very, very simple, that our brain makes unconscious inferences about how we perceive the world. So we make assumptions, and these assumptions at the end become biases. And something is very simple, and you can think evolutionary why this happens. Because the sun is above, because the moon is above, we expect the light comes from above, right? And because we are social beings and we are used to talk to people, we expect that a face should have the eyes on the top and the mouth in the bottom. Everything upside down would look weird. And of course, the same thing happens because we have two eyes and stereo vision. We expect that if I put my hand right in front, it will cover some of you. So distance dictates occlusion. And a very key element in how we understand and perceive the brain and how it works have been optical illusions. Now, I'm a huge fan of illusions, and I have collected many of them to show you today, but I'm going to show you only one. One that actually tackles our assumption that the light comes from above. This is one of my favorite ones. They look like two squares, like two chiclets, you know, if you like gum. One is supposed to be, it appears at least to you, darker than the other, and you see a shadow. But if I place something in the middle, you will see that the color is actually identical. This is a perfect example of how your bias affects what you see and how you perceive the world. As technology evolved and our understanding of the brain with neuroanatomy worked, we start having a little bit of better understanding about how our brain perceives information. And this happened thanks to work of his and Dieter's, where they found some pivotal components of how our brain is composed, okay? We still don't understand how the brain works, definitely not the Greek brain. But it's composed by neurons, and these neurons basically collect and commute information, and they do also some nonlinear processing. Why do I present them today? Because they have been key in inspiring how we come up with some of the first machine learning algorithms. And the most well-known is from the 60s, from Rosenblatt, who used actual neural networks, real neural networks, as a way to get inspired in designing neural networks with electronics, with actual circuits. The information here gets input with X's. The X's represent voltages. These get basically weighted by some components. They get summed, and then through a nonlinearity, you can make binary decisions, okay? So remember, 60s, something very, very big that looks like what you see on the image there. In the late 70s, we had a very important invention. We know how we wanted to have something that can collect visual information, right? We have our eye, so we wanted to find an analog. And that analog came with having the first digital camera, okay, invented by Steven Sasson here, working at Eastman Kodak in Rochester. So a very, very big camera that will be able to record information digitally on some storage medium. And now the information of the world can be captured beautifully within a digital form. And I want to show you one of my most liked pictures. This is a betta fish. We have one at home. But as we will zoom in, you will see the fundamental element that makes up all of the beautiful pictures that we see and we use today. So that fundamental element is called the pixel, shortened for the picture element. There is a lot of additional information that you see. You can really see the discrete structure that exists around, like nothing is continuous, right? There is jaggedness. But also, you see that if you focus on the pixel that I'm pointing with a yellow arrow, all around things there, they look a little bit similar. So that similarity creates redundancy, and this is something that we have to remove as a way to do better image processing and computer vision. Now, you see here a very beautiful kitten, right? We are able, as humans, to recognize objects almost effortlessly. But to the computer, everything looks actually like numbers. So one of the first attempts to try to understand how we can do machine vision was to think about how we would interpret elements of that picture. So maybe when we see the eyes, things look like a circle. Or when we look at the triangle or the tip of the ear, we say things look like a triangle. So some of the first computers were very poor, had very little memory, and some of the first cameras were actually black and white. So we will basically look at something like this and try to extract information from something like this. So this type of notion started to what we think having of how we go from patterns to try to create a way to look for these patterns. So let's say we have an image that has a triangle inside, and we're trying to look for the triangle. We will create a library of possible triangles, right? Different sizes, different rotations, and then we will look around for the best match. It works okay for a triangle, might work well for some other rudimentary objects like a circle or a square, but things will become more complicated when objects will overlap. So you can really see that these things very quickly became impractical, and somehow the field basically stopped at using computer vision just for industrial applications until the early 80s. Another critical thing happened at the late 70s. And I was born. I was born in Greece, in Thessaloniki, in the northern part of Greece. I enjoyed food early on. As you can imagine, it's been the same, nothing has changed. I got my name from my grandpa, Sotirios, that you can see in the picture. I lived for a while with my mom and dad in North Carolina, Raleigh, and then after a few years there, we moved back to Greece. I've changed haircuts since then. And this is also a picture of my sister Maria being there like a little baby. I'm not photogenic, you can really tell. I always look the wrong way, close eyes. I don't like cameras, although I work with vision. Anyway, I went to a very nice elementary school and high school in Greece. It was public, meaning like, but not private. That was called the Experimental School of Aristotle University of Thessaloniki. Is a mouthful. It is the practicing ground actually for students that, like undergraduates and graduate students that want to learn to become teachers. So you will get exposed to a lot of different things, including new types of I'm going to try to say pedagogical methods. And the school was actually very advanced. We had a lot of science experiments, physics experiments. It was very interesting. But there was something that shaped also my life, was I think one of the first students to have a personal computer at home. And that was thanks to my dad's job as an academic that I was exposed to the advances of technology. Something more empowering was the fact that I read an article about the mysteries of the Antikythera mechanism. This is a very famous object in Greece. It was found in a sea wreck, and effectively it's an analog mechanical computer, almost 2,000 plus years old. And it calculates the movements of stars following this metonic calendar. So I read about this metonic calendar, and then I found out that this metonic calendar was invented by this guy called Meton of Athens, who was considered to be one of the first engineers. And then I'm like, okay, I'm going to name my computer Meton. But I didn't know whether I wanted to be an engineer yet. Until much, much later in high school, I was actually wanted to be a volcanologist because I liked things that go boom. I also played the drums in a metal band, so I thought I would become a drummer. But what changed my life, actually, was I met an undergraduate student at the university. So he was a first year actually undergraduate student. And I told him, I'm thinking about going to engineering. You should definitely go to engineering. We teach all of these new things, and we have all of this stuff, and we can, we touch electricity, and you can die, but it's okay. So he was very excited. And I think that's a lesson for those that are listening, the students here, that feel free to talk about what you do. You can actually change somebody's life, okay? So offer your experiences, even if you're not asked. And just don't tell them that things can go boom, okay? Anyway, moving on. As I was growing up, other things happened in the field, in machine learning and computer vision. Images got bigger, better, and then we quickly realized that if we want to process them, we have to remove some information, okay? We want to remove this redundancy that exists. But the computers were still not good to process these big images now with full color. So one of the first things that we will do will we break them into images, into small patches, into small pieces. And then we will process these pieces individually. And we will basically try to see how can we remove and keep only the necessary information for each small piece, for each small square, as a way to try to make sense of what we see. So the interesting thing that happened was that we were able to come up with a simple approximation that we can linearly combine fixed squares that I show you here with orange to basically recreate one of these interesting patches. So we will basically rewrite the input as a linear combination of something fundamentally that we know how it exists, okay? And we will use mathematical transfers to do that. The interesting thing here is not the squares, is the x's, because we call these x's features or representations, okay? Now, one of the most famous transform is called the discrete cosine transform. It's the one that actually you use every day, as long as you take a picture. It's called the JPEG. It's part of it. Or if you still have a DVD, it's part of MPEG-2 within the DVD codec. But this also empowered how we do machine vision. So, and now we also were able to combine it with machine learning. So we will take an image of a kitten, cut it in pieces, not the kitten, extract features, basically try to remove redundancy, and then we will collect some data. We will collect some data of the dog. We also have a live one right here. You can see her later. Or a picture of a cat. And then we will use this data and then say we can fit a classifier, like use any machine learning algorithm that you like, even a perceptron like the one I showed you before. And then we will try to use this in the wild. So you will try to see on the training data, and then you will try to get a new image and see how it works. Not always things work perfectly, right? You can get a very, angry cat or a shark. So, but a lot of progress had been made already, and that kind of like unlocked a lot of things about, rather than trying to create algorithms to recognize objects, we're basically now teaching algorithms how to recognize objects. Other important things happened towards the beginning of the millennium. I decided to do a PhD, and I was already working in Greece as a researcher at CERT-ET, is one of the Greece research centers in information technology and computer science. And I wanted to do a PhD, and I decided to go to the US, maybe the calling of living there before returned. I didn't have actually very good grades, but I had a few publications, and I was very lucky to actually meet my future supervisor at a conference, and I chat with him, and I told him, I said, I want to do a PhD. I'm still good. Take me, please. Anyway, and I was very lucky to go to Northwestern in Chicago. This is the picture of the bean. It's a very nice statue there, structure there. And I wanted to do the PhD with Angelos in image and video processing laboratory. This is very key why I spell it out, because you will see now. I was not happy actually continuing to do what I was doing before in research. So I used to work before in video compression. And I was convinced that the computer will be a failure, that we will have no computers in 5 years. So I shouldn't be doing any more research in computers. I shouldn't be working in digital form. I should be thinking about the future. And I was convinced that the new way to do things will be DNA molecules and chemistry. So I read an article by Len Adelman at Scientific American that said, like, you can use DNA molecules to do computing and store information. I went to Angelos, and after 1 month that he accepted me, and I started there, hopefully he hasn't regretted. And I said, listen, Angelos, I want to do this PhD on this problem. And he not only tolerated it, but he said, you know what, go ahead, please go ahead. And then we both got passionate about this problem together on how we can represent digital signals as molecules. I did many things in my PhD. This is a slide exactly out of my PhD exam. Definitely, I had not learned how to do PowerPoint by then. As you can tell, it was very ugly, wrong colors, not colorblind proof. But a lot of interesting things happened, that we were able to do so many things on how we can take information, rewrite it into DNA molecules, try to synthesize these DNA molecules, find the correct solutions for how these DNA molecules can survive and stay long-term, and at the same time come up with mechanisms that you can retrieve information. So you can think of the system as a storage device that has tiny computational power. But other important thing happened. We were able, during my PhD, to identify basically a binary classifier that we can do in a molecule. So we were able to find and create a hairpin structure on a DNA that will only activate if it finds a right match. So you can think of the structure as basically having the input, and the output is basically the thing opening up. And that input will only activate when you identify certain mutations on a gene or certain viral sequences. So we were very, very excited as a way to actually create a diagnostic tool with DNA and identify rare mutations. We patented this. We raised funding. We created a spin-out. I kept me employed there further after my PhD. But very, very quickly, other technologies kind of prevailed, and the 2008 financial crash in the US killed all the dreams. And that was a very, very, very difficult part of my life. Everything I worked for and I believed kind of went upside down. And I think I got lucky in several ways, and you will see later. But one of the greatest things that happened to me is meeting Christina. So we were suffering together. She was trying to do her PhD. I was trying to rediscover what's my next dream. But I also realized that you need to be prepared for when luck comes to basically grasp the opportunity. So I really favor this quote by Seneca the Younger. I promised I'm not going to say the Latin. I can barely speak English, so you don't want to hear me speak Latin. And anyway, anyway, moving on, new day, new opportunities. So this started completely random, and I mention it because there is an impact of my life after. So we got into a new collaboration with the artists of Chicago to basically see how we can extract information of digital pictures of paintings. This is a painting of Matisse or of Picasso. We've done work with both artists to see how we can bring color life back to black and white photos. So in the middle, you see a black and white photo of the same painting before Matisse changed it. He got upset with a donor, and he changed the painting completely. Okay, so, but we had these archival photos, and we wanted to bring life back to them. So effectively, this 2-month, summer project turned out to be a 2-year work. But it brought actually lots of interesting experience and lots of great visibility out of this. And it had a very important impact after. So that's a lesson, basically. Don't be scared to take some chances, even in things that don't really matter immediately. You never know when they might be important. Another great opportunity, again, happened completely random. I met a very young assistant professor then, who had just started his career in the medical school. And Rohan, we were basically very similar. We both started our academic positions at the same time. The difference is that Rohan was much better. Rohan is a polymath. He has several degrees. I'm sure if he's listening, he's going to get blushed. And he taught me a lot of things about medical imaging and cardiovascular disease and why it's important that we do early detection, because every second counts. So I got really get into this medical imaging world. And luckily, a few months after we started, Rohan had this crazy idea that got funded with lots of support on how we can use MRI to measure oxygenation in the heart. So that thing that you see on the left side is the heart muscle. It's called the myocardium. That red thing that pumps is basically the muscle, the pump. So you want to be able to see how well it gets oxygen, because if it doesn't get oxygen, it means it doesn't work very well. So you would like to see from the picture to extract some information about how much the intensity changes as you move through the cardiac cycle, as the thing pumps. But you can see the images are not very clear. No information can be extracted unless you do some signal processing to isolate the signals. And after so much work, we were able to demonstrate that you can actually detect differences of oxygenation as the heart muscle pumps. You can detect differences whether you're healthy or you have disease. So that was not easy work at all. It involved animal experiments. Some of them actually I had to do. Very long hours working after midnight. HR didn't care. Scanning, analyzing data until 4 a.m. in the morning, because the scanner time was cheaper after 8 p.m., after the patients have left. So, but I was really hooked in the idea of how can I work in areas of social good where the data actually are precious, okay? Now, other things happened. The community started to move into basically how we can do better computer vision and better machine learning. But at the same time, with Christina, we decided to move to Italy. And I was lucky to get a job there together in the same university as Christina, not because I used to do only cardiac MRI, but because I also did art, because the university in Italy wanted to establish also a digital art preservation and conservation program. So the fact that I did both, and that pro bono work that you saw with Matisse turned out actually to be the kind of the extra thing that as a candidate I could have so I can get the job. Now, one critical thing that happened in machine vision is that now, rather than using fixed features that we can extract, we can actually learn the features directly from data. So an even better approximation is to basically now use a linear combination of learned bases. Notice that I changed the color. These blue squares now are learned directly from the data, and they can do a better job. Okay, they can better approximate the data. Now, another thing that happened here was that we had fantastic theory from the work of Candace and Tao that basically were able to show algorithms that can best extract these squares using the least numbers of them. So we had the best square design, the best learned bases, and also the least number of weights that you can use, like the sparse number of weights. As I was setting up my team in Italy, I was very lucky to have lots of excellent PhD students and postdocs there. And one of the problems that we tackled first was how do we use these same ideas as a way to solve a problem in a very common problem in cardiac image analysis on how we can segment the anatomy. So how can we go from the black and white image that you see on the left to the color one that you see right here. So where every color tells you a part of the anatomy. So this is called segmentation. And of course, here we use the same idea. We use templates that we learn directly from the data. And as you can see, this looks like pieces of a donut. And the myocardium looks like a donut. So you can think of it like it's pieces of a donut coming together. Now, we did a lot of other work with also Marco, Christian on other aspects, but that's a story for another day. Very quickly, you will realize that I don't do one thing. I like to do several stuff. And I got really obsessed with this thing about agriculture and plants. For two reasons. One, because I really believed that without good nutrition, it doesn't matter if we have very good health, and it doesn't matter if we have the most advanced MRIs in the world. We still need to be kind of like belly full and healthy. And the second thing is that my father, who's a plant geneticist, used to say, the climate change is coming. We need to study how plants will change subject to environmental change. So that kind of registered. I wrote a grant, and I kind of fascinated to be building affordable devices that we can image and monitor plants. We started growing our own plants in the lab. We created software. We did a lot of different things. And we made a promise that whatever we do, it will be open hardware, open software, and open data. Lots of brilliant people at my group then helped, including Valerio, who should be somewhere here in the audience. And we basically tried the first machine learning algorithm that can go from an image directly to counting the number of leaves. It was not possible before. And we continued this success later until today, working also with several colleagues across the world. And again, here you see this idea of patches and trying to break down the image into pieces. More recently, actually 10 years ago almost, the deep learning revolution started. And I'll explain to you a little bit what that means. But also we moved as a family to Edinburgh. The deep learning revolution is actually something it sounds complex, but it's actually very simple. If you remember the discussion of the perceptron that I showed you before, the neural network, so now basically you're doing neural networks at the extreme. Too many, so one after the other, one processes the output of the previous one and so on, and effectively trying to learn hierarchies of information. The way you train is as before. You give examples of the input, but now you use full pictures, not just squares and patches, and you have a desired output, and you are successful. You basically train an algorithm. But to train these machines, you need lots and lots and lots of data. So when I came in Edinburgh in 2015, we were already talking about that you need 1 million inputs, 1 million images with a desired label, the desired output, as a way to train these machines. So I quickly realized that this will be impossible for applications in AI and machine learning in social good. So I set up the team here that we call VIOS, means life in Greek, for effectively seeing how we can do more with less. How can we train AI inspired by interdisciplinary applications of social good and social importance, that we will be able to do so with less data and less annotations. And that became our ethos since the start. And we started with a very important problem, that not all scanners are the same. So if you take different scanners and you take a picture of the same anatomy, these pictures will look very, very different, okay? So one of the problems that we started first was how we can combat this variation that different scanners introduce into how images look like without lots of training data. I was, again, very lucky. I think that's the 11th time I said that today. That Agis, who should, hopefully he's in the audience, was one of my first PhD students, and I had also a postdoc called Tom. Tom is very, very shy. It's impossible to find a picture of him on the internet. But he's there. Imagine a circle. And we started and both of them are now flourishing scientists actually in industry, right here in Edinburgh. So we thought of like, how can we train an AI to basically separate information that comes from the sensor characteristics, right, versus information that comes from the patient, like the patient anatomy, the patient's disease. And we worked a lot on this problem. We came up with several models that we can train AI with even a fraction of the annotation effort and fraction of the images that we really need as a way to get good performance. And we beat the performance of all the other algorithms there that will use more and more data. And in fact, for this, Agis was nominated for the Early Career Award of the Society of Cardiovascular Magnetic Resonance. For the group and for me personally and the team, had a much bigger impact. It basically became the basis for this trilateral collaboration between the university, Canon Medical, and the Royal Academy of Engineering, who Jorge, I think, is also here in the room. And this funding basically allowed us to focus for 5 years on trying to solve very important problems on how do we scale up doing more with less. So one thing that we positioned and put there in 2019 was we shouldn't create simple models, we should create one big model, one big AI that can solve for several types of inputs, several types of tasks, and try to do like the human brain. We solve many things. We're supposed to be multitasking machines. Christina will say no. And today, we call this type of models foundation models, okay? But that's work that we've been doing and started to do from early on. I don't want to bore you with all the things that we've done scientifically, but I just want to show you that this kind of model of triple helix model of innovation does really work. Once you have the right partners together, we've done lots of people exchange, people from Canon coming here, people from here going to Canon. We trained lots of PhD students in topics of interest to Canon. We published really well, some of them also being award-winning work. We filed patents, and also, despite the fact that we did all of the work within basically during the pandemic, we disseminated everything. We tried to do lots of different outreach and so on. So I think instead of me telling you, I think how the impact of the work, I think I'll give the floor to Takada-san, who will give you.
Canon Medical System is proud to be working with the University of Edinburgh and Professor Sotirios in particular. I'm sorry I couldn't attend this wonderful ceremony in person, but on behalf of Canon Medical System, please let me offer my sincere congratulations to Professor Sotirios. Our collaboration up to today has been great and has led to very fruitful outcomes such as multimodal AI and learning with fewer levels. These outcomes will be applied to our system for creating interpretation report. As medical imaging and diagnostics is an important area in the healthcare field, we hope to further new innovation in this area with the help of you. I'm looking forward to working with you more in future, particularly with the new AI Hub Chai project. Thank you very much for your attention.
One thing that really wanted to solve is how can we create an AI that should be able to predict and suggest treatments. So I want to give you here an example. So let's say that we have patients that have come to the hospital with a pelvic fracture, and we collect some data about their characteristics, let's say their age, their gender, and so on, and we want to use this historical data as a way to predict the risk of disability after 3 years. Solving this type of problems basically has become my biggest challenge. So now we can relax and we can talk about the picture on your flyer. So hopefully you all have one, right? And this picture has been generated by an AI. It's called the DALL-E 3. You give it text and it produces an image. So if I say the astronaut riding a horse in a photorealistic style, you get this, right? Now, we will do an exercise as a way to basically motivate the biggest challenge. So this is the picture that you have on your flyer, all right? And the exercise that we will do together is to try to guess what is the text I used to generate the image. And rather than doing it like a classroom, where you raise your hand and you try to say the whole thing, we will do it the way we do the lecturing, using advanced websites. So get ready, get your mobile phones out, right? There is an exam after too. So we will do this exercise. You can take a picture of this QR code, or if your phone is not very, very smart, you can, mingle. You can go to the website called wooklab.com and enter the code. Okay, success. Yes? And you should be able to see this. And you can vote. I'm going to hide it so you don't get influenced, peer pressure, for 2 minutes. And then you can vote and think about what sort of word I used as a way to generate, what sort of key sentences I used to generate this text. And then I'll prove you all wrong. $160. You can use many options, as many as you want. Okay, I think we are converging. That the majority of people believe that I use the word pixelated. That's correct. Sounds like a video game, like on one of the TV shows, right? The majority of people said that I used the brain MRI. Some people think I used brain and neck MRI. Yes, clearly that's a woman. And a lot of people thought that I actually said a beautiful woman, and only 9 people said that I used a non-white woman. So this thing will still run, it's okay, but we can continue with the presentation. Now, it turns out that this is the text I used. So left half should show a woman's face pixelated, and the right half be a scan of the brain and neck as if it has been acquired via an MRI scanner. The woman should look straight and preferably not be white. Background should be black. MRI image should be realistic. I don't know if we have any neuroradiologists in the room, but probably they will tell you, he's not paying attention, that it doesn't look like a realistic MRI. Then you will say, well, if you want to fix the problems of that image, I actually didn't want the woman to be white. I didn't say beautiful, okay? Why not you fix the text? And this is my attempt here, trying to fix the text. There was a video here that will play there you go, play, of me trying to fix the text. I will try to say, I will add the words and I'll say it's something, change something. It seemed to be very, very hard to not get a beautiful woman. It seemed to be very, very hard to get a black woman with a realistic MRI that doesn't look like a monster. It was very, very hard to get a Maori woman there, and it was very, very hard to also get an Asian woman there. And some of the images look completely weird and scary. So you will wonder why there was a bias towards beautiful. Because these machines, these AIs have been trained on public data, the data that you find on the internet. And most likely, the images of faces of beautiful models exist from the magazines that basically create the digital media. So it turns out that if you want to fix these biases, you have to fix them by hand. But it still doesn't work. This is an example of Facebook's Meta AI Imagine tool, where somebody said, give me a picture of the founding fathers, and they got this picture. Now, I don't want to get into politics or history, but founding fathers were white, unfortunately. It's very likely here that the AI was influenced by all the images of Hamilton, the musical. And unfortunately, trying to break things and fix things by hand, effectively you break causal historical relationships. So going back to that picture that I showed you before, now imagine that some groups of the population do not like to go to the doctor, and they go much, much later. They're in pain and they go much, much later. And imagine that now you collect all this data, and you collect also the information of this subgroup of populations. You will effectively, if you train a simple AI to predict the future of risk in 3 years of disability, automatically will say, if you have these characteristics, you will have disability guaranteed. That has nothing to do with the person's individual aspects. It just happened that because they mistrust the healthcare system, they just go much later to the doctor when things are worse. So training a current AI on this historical data effectively will make very big mistakes in prediction because of data biases. And actually, these are all examples of how current AI effectively is failing us within the healthcare system because of these data biases. And these data biases happen more and more and more because we collect more and more and more data about each individual and each patient. And in big data, it is easy to find correlations. We can all agree that eating more mozzarella cheese doesn't make you actually get a degree in the health profession, right? So correlations and the spurious correlations are very, very easy to find. So effectively, the solution here is to do something more, to do basically what we call causal AI, and effectively try to identify additional paths that might affect a decision. So we know, for example, that pelvic fracture it causally relates to disability, but there are other ways that you might affect this path. And causal AI can help us do that much better. We've been doing lots of interesting work in causal AI within the group. Here I only point some examples. Some of them are jointly with Canon. Some of them are with some of my new students in Athens. Lots of interesting work, also patents around this area. But very, very quickly, we realized that this is way too complex to solve on our own. And I basically got on a mission in the last couple of years to see how we can do something bigger and better that basically can devise solutions co-created by a bigger ecosystem if we want to make a difference. And this gave birth to chai, like the tea. It's a multi-million pound effort that I now lead together with several scientists, most of them much better than me, in the UK and the world. And we build a huge consortium there of industry, policy, government as a way to try to make a difference for the future. Now, we're reaching the end. I hope you still have a little bit of strength. My daughter is already ready to clap. So she's probably thirsty, right, Sophie? And I think I want to tell you a little bit about the future through a storyboarding exercise. So imagine that we are in the future, Initially, I had a year, and I so didn't want to have a year. Then somebody kind of go to YouTube and say, "Oh, Professor X predicted this by that, and it didn't happen. He didn't know what he was talking about." So I said the future in general. So let's say we wake up and we walk around a very, very fancy smart home where we have lots of different types of sensors that effectively monitor our health. And there is also this fancy AI that effectively says that, Soto, I detect some abnormalities in your heart rhythm. I suggest you please go to the nearest pharmacy, the nearest Boots, and get an imaging scan done. And there is this fancy imaging booth. It's artificial. That's not a product. There is no disclaimer. It's artificial. It's computer generated. And this kind of like imaging booth, fully automated, tells you like there are severe abnormalities in your heart, Soto. We really suggest that you go to the hospital. And you go to the hospital, and the hospital is completely reimagined. Basically, multidisciplinary teams, in person, remote, they meet together, they work together with AI, they have access to all your historical data, they have access to all your data from the homes, the sensors, and effectively they say, you know what, it's really great that you came. Working together as a team, we think we should change your medication, okay? It's a fabricated story, but I want you to think about everything that we talked about today, how the importance of sensors, the importance of the AI, the importance of making things affordable, equitable, how they will make a difference for everybody. And I'm pretty positive that imaging will always play a role. We now have already affordable ultrasounds that cost about £1,000 that you can connect to your mobile phone and you can use them at home. But imaging alone is not going to be enough. We should be able to integrate it with lots of other types of information. The wearables, although I wear my fancy watch today, but EKGs, other types of text information and so on. So I'm sorry, ABBA, and I'm sorry, everybody, I lied. Is there a presentation that will take it all? And with that, I want to thank you for your time and your attention. I hope it was entertaining. I want to thank my team at the university, VIOS. I want to thank all my university colleagues, the School of Engineering, college, all my colleagues at the medical school, the vet school, informatics, everywhere you can imagine. My Canon colleagues here and in Japan, my collaborators, the funders, the patients that have actually allowed us to use some of their data for our research, and of course, my family. Without them, nothing really matters. Thank you.
That was amazing, Sotos.
Thank you.
And I wanted to say, although Sotos had mentioned that he had many collaborators, and I think you said all cleverer than you, I just want to say that tonight, when I look around in the audience and also online as well, it's just amazing and a real tribute to your breadth and your curiosity that there are so many people here from so many different parts of the university and from beyond the university as well. So thank you very much, Sotos. It's fantastic, everything that you do. The tradition is that we go and enjoy ourselves with food and drink, and we can ask Sotos questions outside. So Sotos, thank you very much indeed.
Thank you, everybody.